Alright, in this video we introduce the Fourier series. And Fourier series are based on a very wild assumption that any well-behaved periodic functions can be represented as a linear combination of sines and cosines. And the Fourier series has lots of practical applications, and also it eventually provided a lot of foundational notions in modern mathematics. So let's start. First, we introduce the notion of periodic functions. So we say a function f of x is periodic if, so this means if there exists some positive real number such that f of x plus t is equal to f of x for all x, which is in the domain of the function. In this case, we say this real number t is a period of f of x. And we can see that if t is a period, then 2t, 3t, 4t, and so on, any integer multiple of t is also a period. They are all periods of the same function. And the smallest non-zero period is called the fundamental period. Let's see an example. For each natural number n, cosine nx and sine nx, these functions have a period of 2 pi. So 2 pi is a period for all these functions. And for each of these functions, we have the fundamental period of 2 pi over n. So in fact, so let's consider this cosine function here. So cosine, let's say f of x is cosine nx, then f of x plus 2 pi is cosine n times x plus 2 pi. And if we expand this, we have cosine nx plus 2n pi, which is equal to cosine nx. So 2 pi is a period of this function. And if we substitute x plus 2 pi over n, then we have cosine n x plus 2 pi over n, and which is cosine nx plus 2 pi, which is equal to cosine nx. And if this constant is less than this value, then it's not, this equality doesn't hold. So 2 pi over n is the smallest period. Therefore, it is the fundamental period of this function. And the same applies to sine function. Okay, now let's define the Fourier series. So definition of Fourier series. That's easy. 1 over 2 is 0 plus n from 1 to infinity an cosine nx bn sine nx. So the series of this form where a0, a1, and so on, and b1, b2, and so on, they are real numbers. Well, usually real numbers. We may consider sometimes complex numbers, complex coefficients, but usually they are real numbers. But anyway, so any series of this form is called a Fourier series. Here, this one half, this factor may look a little bit strange compared to other terms, but this is for just for convenience reasons, which will become apparent later. And as you can see, since cosine of nx and sine of nx, they have a period of 2 pi. So the entire series here, if this defines any function, then this has a period of 2 pi. So as such, we may consider if this defines a function, then we can only consider this function on this domain, either from negative pi to pi, closed interval, or from 0 to 2 pi. Either is fine, or maybe we can use something else as long as the length of this interval is 2 pi. Anything is okay, but usually we use either this or this. Oh, by the way, this x is of course a real variable. Okay, this x. Okay, next, suppose we have a function f of x defined on an interval between, let's say, 0 to 2 pi. And if this function can be expressed in terms of a Fourier series, so that is this, an cosine nx, bn sine nx. Then we say this, the right hand side is the Fourier, or maybe we should say a Fourier series, Fourier expansion of the function f of x. Because we're not sure if this representation as a Fourier series is unique or not. For the moment, let's say a Fourier expansion, not that Fourier expansion. Here, one important question is, if we given this function f of x, and if we know that it can be expanded as a Fourier series like this, then how can we determine those coefficients? And so that's the next question. So let's find out. But before that, let us note some of the fundamental properties of these sine and cosine functions. First of all, if we integrate the product cosine nx times cosine mx dx from 0 to 2 pi, then this is equal to pi times Kronecker's delta, mn. So this is Kronecker's delta. In case you forgot, Kronecker's delta. So this is delta mn is equal to 1 if m is equal to n. Otherwise, it's 0. Okay, so if this n and m are equal, then this integral is equal to pi. Otherwise, it's 0. And similarly, for the sine function, sine nx sine mx dx is equal to the same, pi times Kronecker's delta mn. And finally, 2 pi, the product between sine and cosine. This is always 0. And you should check that. So just use some trigonometric formulas and identities and calculate this integral and show that these indeed hold. If you have studied linear algebra, this may look like these functions cosine x and cosine 2x and so on, and also sine x, sine 2x, and so on, they behave like the orthogonal basis set, right? So if they are equal, then this is 1, and otherwise they are orthogonal, so they kind of they don't overlap. So using these properties, we can determine the coefficients in this Fourier expansion. So that is, if we multiply both sides of this by, say, cosine of mx, then integrate from 0 to 2 pi, then we have, so 0 to 2 pi f of x and cosine mx dx. So the left-hand side will be this, and the right-hand side will be all these multiplied by cosine mx. Okay, but everything will be 0 according to these properties, except when cosine nx, so this n is equal to m. So in that case, the result is pi. Okay, so the result is pi, and in that case, Kronecker delta is 1, so we have uh, 1 here times, and the coefficient is here, that this an should be am because n is equal to m, so am is left here. Okay, and this also applies when m is equal to 0. Okay, so this is 0, 1, 2, and so on. So you should notice that if m is equal to 0, then that is cosine 0, which is just 1. And if you integrate this, just cosine times 1 from 0 to 2 pi, then it will be just 0. And same for this one. And the only term that is left is this one. So we integrate this constant from 0 to 2 pi, and we get just 1 over 2 times a0 times 2 pi. That is just pi times a0, which is just this, okay, with m equal to 0. Okay, so that's fine. And we do the same thing by multiplying both sides by sine mx. And then we have pi times bm for m equal to 1, 2, 3, and so on. So from this, we can determine the values of these coefficients. That is, am is equal to 1 over pi and the integral 2 pi x cosine mx dx, and bm is equal to this. And m from 0, 1, 2, and so on, and m from 1, 2, and so on. And these coefficients, am and bm, are called Fourier coefficients. And by the way, this interval of integration, they can be from negative pi to pi. It doesn't matter as long as the period is 2 pi. All right, so far we have assumed that the function f of x can be represented by a Fourier expansion, this. Okay, now forget about this, and whether the function can be expressed as a Fourier series or not, it doesn't matter, but we can just define these coefficients, okay, irrespective of the possibility of the representation of f of x as a Fourier expansion, okay. So we don't care for now. And then using these coefficients, we can define the Fourier series, okay. So a0, and from 1 to infinity, an cosine nx and bn sine nx. So this is a Fourier series defined by these coefficients of f of x. And we do not know if this is actually equal to the original f of x. We don't know. But we can at least formally define this Fourier series. So this is how we define the Fourier series of f of x. Okay, and also we also write f is, let's say, let's call it somehow related to this Fourier series. Okay, this Fourier series is defined based on this function through these coefficients. And the fundamental question in the theory of Fourier series is that whether this tilde is actually equal or not. And if this can be made equal, then under what conditions this equality holds? So these are the fundamental questions in the theory of Fourier series, which we will explore in this and later videos. Okay, let me repeat the questions, fundamental questions. So under what conditions does this series, Fourier series, converge? So convergence. And the next question is, under what conditions is this Fourier series actually equal to the function on which it is based? Okay, so these two are fundamental questions, and there are actually multiple ways to answer these. And anyway, for the rigorous discussion of Fourier series, we do need Lebesgue integral or measure theory, but I do not require this. Instead, sometimes I just resort to non-rigorous explanations, and we just try as far as we can get without the use of Lebesgue integral. That being said, let me just introduce a theorem and the sufficient condition for this equality approved by Carlson in 1966. So, okay, here's a theorem. Let f be a function that is measurable. I do not explain what this means, but when you study Lebesgue integral, then you will know. Measurable on the interval between 0 and 2 pi, and that is L2 integrable, which means i.e. The integral of this function squared dx is convergent. Okay, so L2 integrable means this holds. Okay, then the Fourier series S of f converges to the function f of x almost everywhere. Okay, so there are some terms which may not be familiar. Almost everywhere. This is actually a technical term, and which I do not explain. So it doesn't. It may not converge everywhere on this interval, but almost everywhere. So it has a precise meaning, but that's left for your further studies. But anyway, that's all for this video, and in the next video and after the next several videos, and we will explain more details about the Fourier series. See you later.